Well, I think we should start. Welcome to lecture on Catalytic Organometallics, part 15. Subject of the preceding lecture, as will be today, is gold catalysis. And this reaction we already briefly discussed at the end of the preceding lecture. Actually, I screwed up the drawing a bit. Please correct it from the preceding script. Here was somewhere a mistake in there. Well, okay, and it was about gold and also platinum. Platinum salts work as catalysts in these cases. These platinum salts and gold salts can activate acetylenic moieties for the attack of a nucleophile. In this case, it is an oxygen nucleophile. The free electron pairs of that oxygen. So, well, let's discuss it with the gold chloride. So, activation of that triple bond. An orate is formed, and an aromatic benzoberyllium cation and the next step, we can understand it as an intramolecular Diels-Alder reaction with inverse electron demand. However, we already learned that presumably this reacts as a 1,3 dipole in a 1,3 dipolar cycloaddition reaction with subsequent rearrangement reaction. Nevertheless, the net result should be an intermediary Diels-Alder type product, somewhat strained, and of course very labile, since this bond, this carbon-oxygen bond, of course, will immediately break, giving rise to the benzylic and allylic cation, and that orate will deliver electrons. And that's all we need for the transformation to the final product. Of course, we still have to deprotect that silyl ether. So all these examples we however to have discussed are activation of acetylenes or some alkanes, I think, and then for the attack of an oxygen and a nitrogen nucleophile. So how about the attack of carbon nucleophiles? One example of an intermolecular reaction of a carbon nucleophile, in that case this electron-rich aromatic system, mesitylene, works as the nucleophile. So you can interpret it as a special type of Friedel-Crafts reaction, a gold catalyzed Friedel-Crafts reaction. 1.5% gold chloride, nitromethane as the solvent, 50 degrees reaction temperature for hours, hoping for this product to be obtained. Well, nothing happens in this case. It's not reactive enough. We have to add a silver salt silver SbF6. So a non-coordinating counteranion. The silver will grab a chloride and a chloride PF6 exchange, and therefore we then have an cationic gold complex, which is far more electrophilic, and this then works very well. 86% yield is obtained, and this is a result from the Rates group, which is located nearby Max Planck Institute for Kohlenforschung in Mülheim. Also an additional activation by a silver salt was applied in the following case. 1% of a gold 1 complex, (1% of silver triflate in dichloroethane, 15 minutes at room temperature. Well, the enolate is formed here, and the enolate has then the nucleophilic carbon at this position. Well, always Markovnikov type addition reaction. That means CC bond formation between this and that position. So a 5-membered carbocycle is formed. And better than 95% yield was isolated. Or for those carbon nucleophiles, you not always need the additional activation in terms of cationic gold complexes. Depends on the substrates, or is it intra or intermolecular. So here the acetylene, this is a cyclohexane moiety. (5% gold chloride), toluene, 100 degrees. This is the nucleophilic center then. Here we will have the electrophilic center. The gold will intermediary be coordinated to this position. And as the final product, this annihilated ring system was isolated and with excellent yield, 97%. So, intramolecular reaction, far more nucleophilic than those we have seen before in this position, higher temperature than normal gold catalysis seems to be sufficient. Well, next example is one of the first examples of a name reaction, the Hashmi-phenol synthesis found by Stephen Hashmi, who is now at Heidelberg University. This is the model compound, 2% gold chloride, acetonitrile, just room temperature, will deliver the phenol (69% yield reported for this case. Well, and you can imagine that the transformation from here to there is certainly a multi-step transformation in terms of a mechanism. It's a one-step synthesis, of course. So a bit complicated, but it is worth to have a close look to that mechanism. So what we anticipate is, of course, the gold chloride activating the acetylenic moiety, CC bond formation from here to there. Well, okay, let's draw that. Okay, I think that's right. So, this is the nucleophilic center. And this is the way the electron density should migrate. Okay, so we have a stabilized cation here, a vinyl orate there. This now delivers electron density. This is the nucleophilic center. This is the electrophilic center. We can combine those, of course, with a three-membered carbocycle, cyclopropane, as the intermediate. And at this position, then a gold carbene complex as intermediate. strained ring system. So, imagine now this CC single bond is broken, a double bond is formed here, the CO bond breaks, and the rearrangement occurs this way. Let's draw that. The structure is, of course, the same as this one. Now you should already notice where the dihydrofuran moiety derives from. So, cis olefin carbene complexes always have a high reactivity. Now we should draw a 7-membered ring system with that oxygen here. Well, and of course, now this is stabilized simply by setting free the gold chloride catalyst. Still, a 7-membered ring system this one. There's a methyl group here. So, an electrocyclization will occur forming the 6-membered carbocycle which is essentially an epoxidized benzene ring system. Well, and this of course easily opens up by acid catalysis. It opens up here the cation, deprotonation here, yeah? So protonation there, it opens up cation, elimination of H plus and aromatization, finally delivers the phenol. Another example, now optimized reaction conditions, even far better yield. So always such a furan is transformed to a phenol. Gold chloride, 2%, dichloromethane, oh no, again acetonitrile. Let's assume that presumably that is not that important, and it was also done at room temperature. Same type of product. In this case, obtained with a 94% yield, isolated yield. You can be sure it's from Hashmi group, that's right. So, another interesting reaction, this methylfuran is combined with this vinyl ethanol ketone and a gold chloride catalyzed reaction, 2% dichloromethane, low temperature, 0 degrees, 7 hours, will first of all connect those two intermolecularly. Or one can discuss the mechanism, might be somewhat more complicated. However, the connection is some kind, you can understand it as either some kind of Friedel-Crafts type reaction or some Michael addition reaction. The reaction takes place at the olefinic moiety, a conjugated addition reaction. Forming this intermediate, which is not isolated, a Hashmi phenol synthesis occurs right with this intermediary product, and well, if we have a look what happened there or there, it should already be clear that this is the product we would anticipate. Well, and indeed 43% yield was obtained, and there are only a few steps more until the natural product synthesis to such a terpenoid is finished. Another gold catalyzed process also developed at the Max Planck Institute for Kohlenforschung, but not from the Rates group, but from Fürstner's group, which we all, of course, know very well. In a few steps, with using gold catalysis, Fürstner's group was able to synthesize, well, 6-membered carbocycle with annihilated 3-membered ring. Well, how did they do it? Well, of course, they had to introduce an acetylenic moiety, acetylide nucleophile reaction with the carbonyl, and with acetic anhydride, the alcoholate is trapped. Then the catalytic gold chloride activates the acetylene. The nucleophilic center will be that carbon. This delivers an electron pair. You will have a stabilized carbocation then there. So, oh. I should better pay attention here because, well, as you see here, I was drawing a 5-exodic cyclization, but we found a 6-endodic. Well, I have no idea why this happens in this case. Okay. So, at least this seems to be the experimental fact. So, and now again, similar to the cyclopropane formation in the mechanistic cycle of Hashmi phenol synthesis, also in this case, a cyclopropane intermediate is formed, while actually then it's not an intermediate, the cyclopropane ring will remain. So the orate delivers the electron density and again we have a carbene complex. So, and now the rearrangement is rather easy to figure out. Also in this case, oxygen nucleophile, just compare with this reaction step here. It's essentially the same. Well, and now, no problem to get to here. Gold 3 chloride is eliminated, and that's it. So the yield from here to there are astonishing 89%. Okay, marvelous reaction. You certainly agree to that. But now, briefly, the highlight of gold catalysis. This is Hayashi's isoxazoline synthesis. Hayashi's group started with an aldehyde and this type of isonitriles were used as the coupling partners. A chiral gold catalyst was applied. Just 1 mole% is sufficient. Dichloromethane, room temperature 20 hours. And the result of that is then this heterocycle enantioselectively high yield and better than 90% enantiomeric excess. Very impressive. Well, you find that in the Journal of the American Chemical Society in 1986. Page 6405. It's worthwhile to have a look at that, and there you will find, well, an intermediary complex which can also symbolize the transition state for the reaction to occur. Well, just before the carbon bond formation takes place. Okay, this will be the nucleophilic center will attack here, and that O- will then connect to that carbon. So, so what one should concentrate then when drawing that structure. We have a ferrocene unit there. Diphenylphosphine ligand sitting here, and also there. In addition, we have a side chain with a chiral center at this position, and, well, 2 basic centers, that nitrogen and that one. Well, a cationic gold complex is the intermediate with a tetrafluoroborate counter anion. That cationic gold coordinates both the carbonyl oxygen and the isonitrile carbon. That substrate is deprotonated here by the base, and it is assumed that that whole thing is stabilized by hydrogen bridging bonds. Well, this is remarkable in itself. Up to date, I haven't seen anything nice and complicated and so very well set up in gold catalysis as this, and well, almost 30 years old. Well, this is certainly chemistry, I would say, of the second half of the 21st century, already invented in the 20th century. Okay. So, a few interesting examples, not impressive like that, of course, but also useful and interesting. I have still on my list. The first one has been published by Fujiwara in the year 2000. It must be important chemistry, since it was published in Science. 1% palladium acetate, trifluoroacidic acid, room temperature 10 degrees. So, and what happens here? This reacts as a nucleophile with this center. Well, it is claimed that a metallation takes place here at that CH group, and the reason why it was published in Science, oh, this is a case of, right, label CH activation. So the result was obtained with almost quantitative yield. Let's compare this reaction to a result with the same substrate. Well, a much simpler reaction partner, methyl vinyl ketone. Then use another catalyst, 0.3% gold chloride, isonitrile, 22 degrees, 1 day reaction time, The same type of reaction product is obtained, reacts smoothly, and well, the same yield, 99%. So, okay, that might be CH activation, but well, presumably it's more. Well, I would say it's still some kind of Friedel-Crafts type process, with then gold chloride as a nice catalyst for this special type of Friedel-Crafts reactions. And well, if we add or use not gold chloride, but each HbF4 etherate, and one equivalent of that. Similar reaction conditions, or shorter reaction times, just 40 minutes. Well, then you get almost the same product, but second equivalent of this is introduced. So you have this here in excess and there also in excess. Yield 95%. So here you have a nice selectivity. The one-to-one product is purely formed. Here you get the 1-to-2 product. So the HbF4 is far more reactive. Nevertheless, here you have that selectivity. And if you would try that type of reaction with more sensitive substrates, for instance azolene, then the reaction works very well and smoothly also to the 1-to-2 double alkylation product with a gold chloride, and with HbF4 etherate you have a problem with polyadducts, here in this case polymerization products. One more example of a reaction which was recently introduced under the label CH activation, published in Angewandte. Same substrate as before, but this time a propagylic alcohol. As coupling partner. So 73% yield with the most impressive ruthenium catalyst with a ruthenium bond and those CP star. This is pentamethyl cyclopentadienyl as ligand. Well, this cluster is stabilized by thio bridges very impressive catalyst. 1% of that is enough for getting that 73% yield. Well, again, sometimes some kind of CH activation is claimed. Well, of course, in Friedel-Crafts reaction, CH groups, aromatic CH groups react. So, and it was tested. What about other more Friedel-Crafts typical catalysts? Well, so same substrates, but two equivalents of VF3 etherate, which one does not have to synthesize like that complicated ruthenium one. You just have it normally stored in the fridge in your lab. 0 degrees, 5 minutes reaction time, and wow, a 95% yield is claimed with the additional remark 1-to-1. So why that 1-to-1? I think you should know. We have here two stereogenic centers, and therefore we have the mixture, the 1-to-1 mixture of the diastereo isomers. And since with the reaction we have discussed before, the gold chloride delivered an excellent selectivity for the 1-to-1 product. This is the 1-to-1 product. Well, okay, it was also tried once again. 0.3% gold chloride. This gives also but in a far better yield, 96% and none of that. So, what you should keep in mind, gold chloride is a highly interesting catalyst for activation of acetylenes, for the activation of olefins, but also for quite a lot of Friedel-Crafts type processes. Very selective, moderate reaction conditions, highly active, so it is worthwhile to think about gold chloride as a catalyst for various cases. Well, that's enough for today. Thank you for listening. Next lecture will take place already next Friday afternoon. See you then.